this is Susie Newhan, and this is differentiation from first principles. So the task at hand is to find the gradient of a curve at any point. So here's a curve, y equals 3x squared, and let's say we want to find the gradient at A, right there. So this is how we're going to do it. You do not have to be able to do this in order to differentiate. Differentiation is actually quite easy, but I think it's really helpful to see what's behind this, and it's such a magical piece of maths, no one should really miss it. So let's say we want the gradient here, so we introduce another point on the curve, because we know all about points on the curve. And let's say it's just a little bit further along the x-axis. Let's say there's a little distance h between the two. So that means that the x-coordinate of B is x plus h. Now we're going to start by finding the gradient of that green line, which is called chord. So in order to find the gradient, we need the change in y over the change in x. So we can sort of see the change in x values, but what's the change in y values? Well, given that we know the function, we should be able to find the y value of b. And in fact, it is x plus h squared. Yeah, so wherever we see an x, we substitute in x plus h, because that's the x-coordinate of b. So using our linear function algebra that we've learned, we can now find the gradient. So the gradient is going to be the change in y over the change in x, because it always is, isn't it? So the gradient, the y values between there and there have changed by this amount. And the x coordinates have changed from, so x coordinates have changed from that to that. The y coordinates have changed from that to that. So if we subtract them, we get the gradient of the straight line. So I'm now just going to do a little bit of school maths and multiply out that bracket to xh plus h squared minus 3x squared all over. I'm going to get rid of those brackets. Right, and now I'm going to multiply out by 3. I want to keep this short, so I'm not going to go into what happened there. Whoops. Oh, messy. So multiply out by 3, we get 3x squared plus 6xh plus 3h squared minus 3x squared all over. And hopefully you can see that the bottom simplifies because we've got x minus x. So the x's disappear. So can we simplify the top? Yes, of course we can, because look, they disappear. So we end up with 6xh plus 3h squared all over h. And we can separate that out into two fractions if we want. 6xh over h plus 3h squared over h. And that simplifies to, that cancels out, we get 6x plus that cancels out with that 3h. So the general gradient, if these two have a difference of h, will be that, but that's not very interesting, is it? What we need to do now is this magic trick, because we're going to say now that we're going to find the limit as h extends to 0, i.e. we're going to keep making h smaller and smaller and smaller and smaller until at some point b is practically on top of a, and whatever that gradient becomes then is the gradient at a, because that chord and that point become the same thing when we've got such smallness. So we take h to infinitesimally small. So what does that mean? Well, that means a 3h goes away. And you probably already know that the differential of 3x squared is 6x, but that's where it comes from. And we can do that with any function. The algebra gets a bit longer, but it's exactly the same process. We use the gradient of that line using this function or whatever function you choose, and it comes down, and that will give you an answer that you will recognise as the differential. So I hope that was insightful. Well done, Sir Isaac Newton.